Hi everybody. This is our lesson on biconditional statements and definitions. So once again, make sure you have the notes sheet in front of you, that you take good notes. The idea of having these videos is you can pause and take really thorough notes. You can rewind and review things that didn't make sense to make sure you have a thorough understanding at a pace that works for you. Okay, what's a biconditional? It's a single true statement that combines a true conditional and the converse is also true. So it's a conditional statement in which the conditional statement is true and the converse is true. And if you'll recall, when we were doing the truth tables in the last, tables in the last unit, it tended that the conditional and the contrapositive had the same truth value, and the converse and the inverse had the same truth value. But every once in a while, you have a biconditional in which they all have the same truth value. The way we write it is by joining the two parts of the conditional with the phrase if and only if. And this right here is the symbol we use for this is only if and only if. It's kind of showing biconditional, that you can either say P then Q or Q then P. Both ways work. But we read it P, and this double arrow Q is read P if and only if Q. So an example of a biconditional is if two coplanar lines intersect, then they are not parallel. So you remember we talked about that. As long as two lines are on the same plane, if they intersect, they are not parallel. And if two coplanar lines are not parallel, then they intersect. So this is an example of a biconditional statement. Both are true. So we can write, and this is falling off your screen a little bit, but we can write P if and only if Q. Basically, two coplanar lines intersect if and only if the two lines are not parallel. So that is a biconditional. So let's get some more experience with this. If the sum of the measures of two angles is 180 degrees, then the two angles are supplementary. So this is our conditional statement. If P, the sum of two measures of two angles, is 180, then Q, the two angles are supplementary. Well, let's look at the converse of this conditional. The converse, if you'll recall, instead of if P then Q, is if Q then P. We convert them. We move them to the other side. So let's see. If two angles are supplementary, then the sum of the measures of the two angles is 180 degrees. Well, this is true. So in this case, we have a true conditional, we have a true converse, therefore we have a true biconditional. And the way we write it is two angles are supplementary if and only if the sum of the measures of the two angles is 180 degrees. All right, I don't know why this true keeps popping up. What is the converse of the following true conditional? All right, if two angles have equal measure, then the angles are congruent. So this is our P then Q, if P then Q. Here is our P, here is our Q. Well, if we're going to write the converse, we're going to switch them, and we're going to say, if two angles are congruent, then two angles have equal measure. And that's true. Not only is the conditional true, but the converse is true. So now we have a good biconditional because both the conditional and the converse are true, and we can write it as a biconditional. Basically, two angles are congruent if and only if the two angles have equal measure. Okay, another one. A ray is an angle bisector if and only if it divides an angle into two congruent angles. All right, so what are the two conditionals in this biconditional? Well, P is if a ray is an angle bisector, Q is then the ray divides an angle into two congruent angles. And you can see that in this biconditional, P then Q works. If a ray is an angle bisector, then a ray divides an angle into two congruent angles. And for it to be a biconditional, the converse has to work as well. So Q then P must also work, and it does. If a ray divides an angle into two congruent angles, then a ray is in fact an angle bisector. All right, let's identify the conditionals again. Two numbers are reciprocal if and only if their product is 1. So you may want to even pause now and try to write down what you think the two conditionals are, and then you can restart the video and see if you got it right. In this case, the two conditionals are two numbers are reciprocal, and then the second one is two numbers whose product is 1. So it has to work for P then Q and Q then P. So let's try P then Q. If two numbers are reciprocals, then their product is 1. Well, that works. Let's try it the other way. If the product of two numbers is 1, then the numbers are reciprocals, and that is true as well. So we do have the biconditional that we've broken down. Okay, now I don't know if you've picked up on this, but part of the reason we discuss biconditionals and part of why it's important in geometry is if you can make a biconditional statement about something, you've developed a very good definition. So a definition is good if it can be written as a biconditional. If it can't, it's probably vague or you've probably left something out. So a good definition also uses clearly understood terms. These terms should be commonly understood or already defined. A good definition is also precise. They avoid words such as large, sort of, almost. You need to be much more precise than that. And a good definition is reversible. That means you can write a good definition as a true biconditional. So let's practice writing definitions as biconditionals. A quadrilateral is a polygon with 4 sides. The conditional is, if a figure is a quadrilateral, then it is a polygon with 4 sides. Let's look at the converse. If a figure is a polygon with 4 sides, then it is a quadrilateral. If both of these are true, which they are, then we can write a biconditional, which becomes a good definition. A figure is a quadrilateral if and only if it is a polygon with 4 sides. And that's a good definition. Now, an example of what would be a bad definition here is you could write a rectangle is a polygon with 4 sides. You could write that. And that's true. A rectangle is a polygon with 4 sides. But is that a good definition? Well, let's look at what the converse of that would be. So if a figure is a rectangle, it's a polygon with 4 sides. That's true. But let's look at the converse. If it is a polygon with 4 sides, then it is a rectangle. Well, there are a lot of polygons that have 4 sides that aren't rectangles. It could be a square, it could be a rhombus, it could be a trapezoid. That isn't precise, and it doesn't work as a biconditional. So this isn't a very good definition. A rectangle is much more than a polygon with 4 sides. It has to have 4 right angles. It has to have 2 opposite sides congruent. There are a lot of other things. So that's why thinking about definitions in terms of biconditionals makes you be precise and develop a good definition. Okay, let's look at another one. A straight angle is an angle that measures 180 degrees. The conditional would be if an angle is a straight angle, then the angle measures 180. Let's see what the converse is. If an angle measures 180, then it's a straight angle. Both of these are true. So we do have a good definition because the biconditional works. An angle is a straight angle if and only if the angle measures 180, or an angle measures 180 if and only if the angle is a straight angle. You could use either one as the first part of the if and only if in the biconditional. Okay, so let's just talk a little bit more about definitions. This one, a fish is an animal that swims. You could look at this, whether it can be written as a biconditional. If it is a fish, then it is an animal that swims. Well, that's true, but if it's an animal that swims, is it a fish? No, it could be a whale, and a whale's not a fish. It could be a manatee, and a manatee's not a fish. So this is not a good definition. It's not precise enough, and it can't be written as a biconditional. So this is not a good definition. Okay, let's look at the next one. Whoa, why did that come up? Okay. Rectangles have 4 corners. This is also not a good definition. The reason being, corner is really not a clearly defined term. Rectangles have 4 corners, so do trapezoids, so do rhombuses, so do squares. That isn't specific enough to tell us what a rectangle truly is. All right. Giraffes are animals with very long necks. Well, they are, but very long isn't precise. What do you mean by very long? And the statement is not reversible because there are other animals with long necks that are not giraffes. So another example of not a good definition. And a penny is a coin worth 1 cent. Well, let's think about that. It is reversible. A coin worth 1 cent is a penny. And penny is defined, coin is defined, worth 1 cent is defined. So this is a good definition. All right, is the following statement a good definition? A square is a figure with 4 right angles. Well, we kind of already talked about this with the rectangle. First of all, if we write it as a conditional, if the figure's a square, then it has 4 right angles. That's true. But if a figure has 4 right angles, is it a square? No, it could be a rectangle. So this is not reversible. It's not a good definition. Okay, how can you rewrite the statement, obtuse angles have greater measures than acute angles, so that it's a good definition? It's really kind of wordy to say have greater measures than acute angles, plus 90 degrees, which is a right angle, has a greater measure than an acute angle, and it isn't obtuse. So it's really better to be specific and say obtuse angles have a measure greater than 90 degrees. All right. The last thing I would ask you to think about before closing here is, Venn diagrams can really help us with analyzing conditional statements and biconditional statements. And I want you to think about that. I want you to draw some Venn diagrams where you've got conditionals that aren't biconditional versus conditionals that are. And I want you to see the difference. And hint, you might want to know that or think about that before coming to class tomorrow. So see you guys tomorrow.